Is it Weiler-Weil pairings? Is that a thing?
W-E-Y-L.
Yeah.
Yeah.
That's
Okay. So, Sylow theorems. It's our last chapter. And
I thought the first week was Monday. It's lecture one.
kind of the combination of the course. So, we're going to start by reviewing a few of the things you've done already, giving you a setting to think about this, right? So, our first nice results was, of course, Lagrange's theorem. Now, I'm hoping we all have a good understanding of that. What did it say? It said, if the group G is finite, G is finite, and H subgroup of G uses compact notation, yeah. H less than G in it's quite fun with this. So H is a subgroup of G. Maybe, yeah, won't be restricted. Any subgroup, maybe the whole subgroup. Then the conclusion was that the order of G divides the order. So the order of H divides the order of G. G is the big thing, H is the small part of it, the small subgroup. Everybody okay? So it restricts the possibilities for subgroups. E.g., if we knew that the order of G was 15, it might, or the order of G is 15, any subgroup that G has, the only possibilities for its order are 1, 3, 5. 1 is the trivial group, exists. 15 is the whole group G, which is clearly a subgroup of itself. And maybe it has a subgroup of size 3, 1 or more. Maybe it has subgroups of size 5. But it absolutely cannot have a subgroup of size 7 or 8. They violate Lagrange's theorem. So it's natural, so a question arises. Does G have a subgroup of size 3? So talking of this example of a group of size 15. It might have, it doesn't violate Lagrange's theorem, but does it have? Lagrange's theorem doesn't make any positive assertions about there existing a subgroup of size or of size 5. I mean, we know it has one of size 1, the whole group, size 15, the whole group. But the intermediate, the proper subgroups, proper non-trivial subgroups, we don't know. Okay, that was one of the themes in question 1. So if a group always does have subgroups showing all the possible sizes, all the possible divisors, then it's called Lagrange. Okay. It turns out the dihedral group, Dn, is Lagrange. It has subgroups of all particular sizes. So e.g., Dn, for n bigger than or equal to 3 at least, is always Lagrange. It has subgroups of all sizes. Another important case was abelian groups. If abelian, then yes, it does have a subgroup. does have a subgroup. Subgroup of all sizes. Does have subgroups of all sizes. That comes from the fundamental theorem of finite abelian groups. The fact that any abelian group can be written as a direct product of cyclic groups of prime power order. So whatever the size the subgroup is supposed to have, you look at its prime factorization, and then you can find a factor of that size between that power of the prime within some of the cyclic subgroup factors that appear in the direct product expression for G. But for general groups, for non-abelian groups, of which Dn is non-abelian, but for your general random non-abelian group, the question is open, or the question still stands. And another important example, e.g. a 5, what was the example? Standard example of a subgroup, of a group with no subgroup of a particular size.
12.
Huh?
12.
Yeah, yeah. So it was A4. A4, which has size 12. Well, A4 has no subgroup of size 6.
And A4 is the alternating group.
Yeah, right. Index 6. So A4 is half of size of S4. S4 is size 4 factorial, which is 24. So divided by 2 is 12. So 6 is a factor of 12. Lagrange's theorem would allow a subgroup of size 6, but there isn't one there. The Sylow theorems supply positive answers to these. Give positive answers to these for certain divisors. I won't dive into saying exactly what it is yet. For certain divisors of size of G. Sylow theorem is based only on knowing what the size of G is. For certain divisors of that size, they say yes, there has to be a subgroup. What the hell? Why don't we look at the statements just to see what kind of results they are? Okay. I'm pretty okay with that setup. Give positive answer to these questions for certain divisors. But they don't say every group is Lagrangian, we know it isn't. Yes, and say 4, so group size 6. But for certain kinds of divisors, they do. So let's look at the statements of the theorems. So we'll look at the state, and I think we can read the statements of theorems without knowing any of the technology. Yeah. So, divisors of order G. So there's 3 of them. The first one says a G be a finite group. Any prime, well, basically any prime that divides the order of G. And indeed, we can talk about any power of P that divides G. It says, yes, G will contain a subgroup of that size. So the answer is yes for divisors which are powers of a single prime. It's the fundamental idea that Sylow theorem talks about. Okay? So this doesn't apply in the case of A4, because A4 we were looking for a subgroup of size 6. 6 is not a power of a prime, it's a product of 2 distinct primes, 2 and 3. The answer is yes when the divisor that you're talking about is a power of a single. Okay? So that's quite interesting. Yeah. But it doesn't rely on any other assumptions about G other than p to the r is a factor of the size of G. So it applies to every group for which that. So abelian, which we already knew, non-abelian, no other information is needed about the group G in the statement. That's the first Sylow theorem. The second one, so there is at least one subgroup of that size. Other questions that arise, okay, well, how many of them? One, but there's multiple of them. Is there any way that we can kind of describe the range of subgroups of that particular size? This is what the second and third theorems go on to say. Well, the second theorem, we'll forget about, it says, so a Sylow P subgroup, when we say, so this is a terminology, a Sylow P subgroup is a subgroup of G which has maximal size, a power of a certain. So you look at the size of G, you look at a prime that divides that, you look at the highest power of it, the full power of the prime in the prime factorization of the size of G. What we call a Sylow P subgroup is a subgroup of that size. It's guaranteed to exist by the first theorem. The second Sylow theorem asserts that all of those subgroups are conjugate. So conjugation, remember, this general construct of multiplying on the left by an element, multiplying on the right by the inverse of the same element. So if P1 and P2 are two such Sylow P subgroups, so they're both subgroups of size P to the R, where R is the full exponent of P in the size of G. Pretty clear on that idea, the maximum power of P that goes into power of G. So in the case of 15, it was 3 to the 1, 5 to the 1. In the case of 100, group of size 100, it would be 2 squared times 5 squared. So you'd be talking about groups of size 2 squared, groups of size 4, and groups of size 25. Maximum power of the prime 5 as it divides on it. Maximum power of the prime 2 as it divides on it. Well, it says if P1 and P2 are two such subgroups, then there is some element such that P1 is a conjugate of P2, and vice versa. Yeah? So you can conjugate one of the subgroups. So while there might be more than one Sylow P subgroup, they're all related through this operational. So that says something about how all the Sylow subgroups are related to each other. And then the third theorem gives us numerical information. Quite useful, interesting numerical information. So again, it's talking about the Sylow P subgroups, so these subgroups of maximal prime power size. It gives you two key pieces of information about the number of them. The number of them that there are, just the count of the number of distinct subgroups of this size. It's congruent to 1 mod P. Okay? And it also itself is a divisor of the size of G. Yeah? So G could have loads of these subgroups. So say our group of size 100. It will have, by the first theorem, at least one subgroup of size 25. Okay? But it might have many of them. What the third theorem is saying is that the number of them that there are, the count of the number of these subgroups, is congruent to 1 mod 5. It's either 1, 6, 11, 15, 21. Be one of those options. Congruent to 1 mod P, but it also must divide the size of G. How many of the subgroups of size 25 are there in the group? Size 100? Well, no, the number of them must be congruent to 1 mod 5. 5 is when you talk about group size 25, P squared. 5. So the number of these subgroups of size 25 must be congruent to 1 mod 5. The options for them are 1 of them, 6 of them, 11 of them. but it must also simultaneously divide the size of G. And the option is 1. So the third theorem actually says there is one subgroup of size 25, size 100. That's quite a lot of useful, one size. Those are some of the ways we're going to use the theorem, drawing those kind of things. So that's a quick look at the three theorems. So we're going to work our way to the proofs of these. Do you have some kind of feeling of the statements of those kind of things they're saying? Okay. Okay, so we think of it as a question leaping off from Lagrange's theorem, except it's going in the other direction. Here's a divisor of the size of the group. Does it have a subgroup? Now, the key tool is group actions. We've just been discussing with Jan last few weeks. But I just want to remind you, just bring to mind again some of the key points about group actions. And then we'll hopefully prove Cauchy's theorem, which is a kind of intermediate step to see the first Sylow theorem. Okay. So a group G can act on a set X. Group G, it's got elements E and some other elements. Here's the set X. Some kind of mathematically meaningful set. A bunch of elements in it, right? So what is a group action again? We've got to remind ourselves what it is. It's a way of saying, given any element of the group, it becomes a function. More than that, it becomes a bijection, permutation of the set X. By, writing this action G applied to X equals Y. Tend to maybe drop the brackets or. Your set X, often said what it is, just some kind of mathematically meaningful set. Might be acted upon by group G, which means suddenly all the individual elements of G become themselves, they turn into functions on the set X, bijections of the set X, also called permutations of the set X, so one-to-one and onto mappings set X to itself. And we write it like this: G applied to the element X, so the element X is one of these elements in here. G applied to the element X is another element Y. Satisfying, so that's the beginning, it must satisfy these nice conditions. The way that the elements turn into functions, it must respect the group structure. Right? So the groupiness that's going on in G must be respected by these bunch of functions. Okay? Groupiness, it's a nice word. Okay, so what aspects are there to the groupiness, right? So there's this special element called the identity. So what kind of a function must that give from X to X? The identity element must give the very special function set to itself, which is the default kind of nicest function. This.
The same thing.
We'll talk about stabilizers in a moment, but just what's, given a set X, what's the kind of nicest function, the nicest bijection from X to itself? What function do we call that? The identity, actually.
I was going to say,
I didn't think I was
the
saying.
identity I was right. That's very super.
Is the identity.
You said to yourself.
Yeah, this is the identity function that E applied to X is always equal to X for every element in the set X. Okay? So whatever way there is of associating functions from X to X to group elements, the function we attach to the identity element has to be the identity function. It must be, because E is the identity element. So the identity is special in a group. What's also special in a group, of course, is the group operation. And this is the only other, yeah, we just must have some kind of associative type thing going on. So if we ask ourselves, which function is associated to the product of elements G1 and G2? It must be the function that behaves like this. So this kind of looks like associativity. It's not exactly associativity that goes on in the group, kind of the equivalent of it in the operation. But the function that is associated to the product of two group elements is the composite of the two functions G1 after G2. Yeah. Yeah, this is for every, the quantifier should go at the beginning, for every x and x, and for every G1 and G2 and G. Strictly speaking, the quantifier should go at the beginning. I.e., G1, G2, this function, the permutation of x to x, this is the function G1 after G2. So composition of functions is a nice operation you can do with functions from x to x. A meaningful kind of way to combine functions from x to x is to compose them. And when you do compose two of these functions, you get exactly the function that is associated under the group action to the element G1 times G2. Now, orbits and stabilizers, this is important. G, here's the set it's acting on. So to any particular x value, you take all the functions that there are coming out of G, represented by elements of G, apply them all to this element, you get a bunch of other elements associated to this. And this subset has a special name. It's called the orbit of x. Yeah. The orbit of x is the set of all elements G of x, where G is an element of G. And since every orbit contains, we index the orbits by the elements x, because E times x is equal to x, every element is in its own orbit. You can kind of think about this dynamically, that this element can hop around to each of these other elements by multiplying it on the left by one of the elements from G. Like a little satellite orbiting around in its orbit. Okay, the thing that makes it move from one place to another is multiplication by one of these things. Multiplication, or the application of one of the functions represented by the elements. So these are orbits. And they partition the set X. You look at all the orbits that there are, some of them be the same. I mean, the orbit of this element can be the same set as well. If all these elements are in the orbit of X, well, the orbit of any of those is just the same set of elements. Comes from these group action conditions. We also have stabilizers. We pick any particular Y here. There'll be a bunch of elements here, including at least the identity, but maybe some others. So the identity times Y is equal to Y. So the identity fixes Y. That first condition group action says the identity applied to any element must just give the same number. So we can say that the identity fixes y or the identity stabilizes y. There might be a bunch of other elements that also do the same. And this is called a stabilizer of y. Stab y, some kind of notation. Stab y, stabilizer y, is the set of all group elements, so it's clearly a subset of G, whereas this was clearly a subset of X, it's a set of all images GX. The set of all group elements such that GY, it doesn't send it anywhere, it's equal to Y.
Does the stabilizer only exist in the group G?
Yeah, no, it definitely belongs on this side of the group. Well, at least it looks it's a subset of G. Actually turns out it's a subgroup. Yeah. So this is a subgroup of G. And one of the key results linking these two things was Theorem 14.11, which gave us a link between these two in that it told us what the size of the orbit of any particular element was. So this quantity refers to the count of these dots inside the orbit of X. Yeah. How many dots are there? It relates it to the size of the stabilizer subgroup. And it's quite simply the index yeah. So sorry, he uses the notation G subscript Y. Talk about the notation there. G subscript Y, the stable, the bit of G that fixes Y. And it's the index of that in G, which is the number, which remember was the definition for the number of cosets of GY and G, which for the case of finite groups is G, simply G divided by the size of the stabilizer. So that's only a valid description when G is finite. Okay. Okay, so that just a quick bringing to mind of some of the things from the previous chapter. Okay, any questions or things you want to clarify? Okay. Now, when we first introduced group actions, we definitely think and try and separate in our minds the set being acted upon and the group doing the acting. But the magic happens, well, when we're going to prove the Sylow theorems and derive things about groups, the magic happens when we merge the two. When we find an interesting action of the group G, not in some other set, but when the set X is G itself. So when G acts on itself. Right? Some of the examples that were in the group action chapter was like where groups of matrices acted on points in the plane. So they were very different. Groups of matrices, points in the plane, two completely different beasts. Matrices act on the points in the plane and send them around the plane. And other examples where you have one kind of thing X and a completely different group of transformations and they act on the. Well, now we're looking at the self-action. So this is where our discussion into section 15.1 heads. The self-action of G on G, self-action. Okay, which one? There are a few. One of the early examples of action of a group on itself you looked at was a group can act on itself by left multiplication. The elements can act on the elements of G by simply multiplying them. Interesting one is by conjugation. Okay. So if you let G be an element of G, this is going to give a function. I hesitate just to call it the same thing. Did they use that up arrow bracket notation? And I kind of want to call it G again. Yeah, I should. It's a function called G, sending the group to itself. Okay. And what does it do to an element? H. G, it conjugates it by little g. So it sends H to G, H, G inverse. Okay, this is an action. Okay. So this is the function generated by a particular element G in the group. And what does it do to elements H from G? It conjugates them by little g. Yeah. GH. It is an action. You can easily verify it's an action because choose the identity. What element you send H to, E inverse, which is equal to H. So the identity is the function that fixes every H. So it is the identity function on the G. Also, if you take a product of two elements, notice that E inverse is always equal to H. And if you take a product of two G's, conjugate H by them, conjugate H by the product. Yeah. So this is the action of the function represented by the product G1, G2. Where do I reconcile that? Well, G1, G2, H. What is the inverse of G1, G2?
G2 inverse, G1 inverse.
Yeah. Product of the inverses, but in the opposite order. And then just by associativity, you can see that as G1. It's the conjugation by G1 of the conjugation by G2 of H. So it clearly is the composition of the two conjugations. First conjugated by G2, then conjugated by G1. So the conjugation by the product is the composition of the two conjugations. G1 after the conjugation by G1 after conjugation by G2. Okay. So it is a proof. So that's a proof that it's an action. Maybe we're not going to get to that. We'll get to establishing the class equation. Class equation. It comes from partition of G by the orbits. Partition of G by the orbits of this action. Now the orbits have a special name and the stabilizers have a special name. The orbits are called conjugacy classes. And the stabilizers are called centralizers. So an orbit of X, orbit of H, right, which is the set of all G, H, G inverse for every little g in G. So it's all of the conjugates of H. That's called the conjugacy class of H. Yeah? Conjugacy class. The stabilizer of a particular element the group G acts on itself. So if you take on the elements in it, we ask what are all the elements of the group that stabilize that element. It's the set of every G in G such that G inverse is equal to H. Well, we often, conjugation is kind of also referring to, it's really orbiting around, for misuse that word, it's hovering around the issue of commutativity. GH G inverse is equal to H, that's the same as saying that GH is equal to HG. So really, the stabilizer of a H is the set of all G's that commute with H. This is called the centralizer of H. So the general terms of orbits and stabilizers have specific terms in the case of the action of the group on itself, or conjugation. Specialized terminology. They are exactly the orbit of a group element. It's been acted upon by all the group elements, and the stabilizer of the group element. And this is on the centralizer, just as notation, is well, the notation we're using is CH for centralizer, C for centralizer. So we'll get to the class equation, and tomorrow I think we'll prove Cauchy. If we pick it up and just continue from the class equation, we can prove Cauchy's theorem in the first Sylow theorem. So what have we got? We've got the group G. It's being acted upon by itself, so it's going to split up into orbits, partitioned by the orbits. Partitioned, except now we're calling them conjugacy classes. Partitioned by its conjugacy classes. Now, your average typical conjugacy class, you definitely maybe think about it as containing a bunch of elements. Yeah? Not like the coset partition, where every cell has the same number of elements. Not that. It's a more flexible partition. There may be different numbers of elements in each cell, right? So all these elements are conjugate to one another. Right? Start at one of these group elements, you'll be able to find an element from the group. Again, it comes from that same picture. But you can find an element from the group, and if you conjugate that element by the other element, you can hop over here. But you can find an element to conjugate by to hop to any of the other things in the same. Of course, conjugating it by different elements might send it to the same image. That's what accounts for there being different numbers of things in each of these conjugacy classes. Some of the conjugacy classes are special though. Some of them contain just single elements. So there are special, in particular, one of these conjugacy classes is the one where just the identity lives on its own. Because when you conjugate the identity by anything, G, E, G inverse, what's that equal? Oh, E. It's always equal to E. So E, you can never orbit anywhere, just only on its own. So its conjugacy class is just E. There might be other elements which are like that as well. There might be other cells in the partition which are just single element. And then there's some other more typical ones which have a bunch of elements. So this is the picture of G, definitely with, on the right-hand side, like the X. It's the thing being acted upon. And it gets partitioned by its orbits. Now, there's a very basic way we think of the number of things in G. Thinking of a partition, we think of the number of things in G as
Some of the things in
Some, yeah. How do we count all the dots? Well, count the ones in this one, add it to the number of ones in this one, add it to the number of ones. So you count by the cells. So it's the sum over the conjugacy classes. The conjugacy classes size of each class. Okay. Very direct idea. So what we do is we let x1 go match his notation here now. I'll let x1 through xk be representatives, meaning one of the elements of your x1, this is your x2, this is your x3, etc. Be representatives of each of the conjugacy classes with size greater than 1. We're assuming G finite here. Finite. So your typical conjugacy classes has multiple elements in it. I'll let x1 to xk be one representative from each of those. Class equation. Class equation of G is this decomposition of the size of G. It's basically just counting the cells in the partition, except it turns out, I don't know if you remember, you should definitely look back in the proof. If you take all the elements that are in these single element conjugacy classes, take all of them together, they are subgroup called the center. Yeah. And then the other ones are, well, remember, each has a theorem 14.11. The size of each orbit is the index in G, or the ratio of the size of G divided by the size of the stabilizer. So the size of one of these multiple element conjugacy classes will be the index in G of the centralizer. And you got one of these terms for each of the xi. What are these all the way to G, C, X, K? Which definitely in the case of finite group G, remember each of these indexes is actually the quotient. And the centralizer. So Z is used for center because it's from the German word Zentrum, German for center. This shows some of the German-speaking origin of this work. And the center of G consists of all those elements X from G, such that for all G in G, X commutes with G. The elements in the center are those special elements from the group, that commute with every element. Okay? So these are commutative elements that commute with everything in the group. Just like the identity, if you are an element that commutes with every element, what happens when you conjugate? So if I have an X in the center, what happens when you conjugate? You do G, X, G inverse. Just equal to X again. Because the X can commute with the G, and then you got the G beside the X at G inverse. So the identity, X, X. So if you're in the center, it means you are an element in your own conjugacy. All of these single element conjugacy classes, we can refer to the number of dots. You see, because these terms only count the number of dots adding up all the number of dots in the multi-element conjugacy classes. But adding up all the ones in the single element conjugacy classes gives you the size of the center. So it breaks down, it gives a nice partition of the size of G as a sum of these terms. And each of the terms is interesting in a group theoretic way. This is the size of a certain subgroup, called the center. Yeah. These are ratios of the size of G divided by the size of a certain subgroup, centralized group. So there's a lot of reference to sizes of subgroups here. And it applies to any group G. Size of the group, we've now suddenly got it as a sum of terms. One of the terms is the size of a certain subgroup. The other terms are ratios of the sizes of G divided by the size of a certain subgroup. Now some of these subgroups might be trivial, or not. There's, possibility. So this thing is the class equation. And this is where it's this central object which we argue off of to prove Cauchy's theorem, is the first one coming up, and the three Sylow theorems. Okay. If you're suddenly talking about primes dividing the size of G, then there's lots of ways to argue about it based on all these terms here, which add together to get the size of G. Because in the numerator of each of these fractions is, if a prime divides G, well, that prime is dividing the numerator of these fractions. So it may or may not be quotiented out or be factored out by that prime appearing as the size of one of these subgroups. So we were going to build arguments that consider primes dividing G, or pairs of primes dividing G, and how they might appear here. Do they divide that? Do they divide one of these denominators or not? So we can build our arguments off of that. So we'll literally continue from there tomorrow. I won't waste too much time reviewing things tomorrow. I mean, I will quickly introduce it again, but